Hello, my name is Marissa Valuri-Rad, and this is my Module 2 presentation. It is going to focus on scale development and hypothesis testing. Scale development is the first topic I will focus on, and the first important concept to understand regarding it is why good measurement is crucial to the social sciences. Measurement is viewed as the process of linking abstract concepts to empirical evidence. Empirically, the focus is on the observed response, while theoretically, the focus is in the underlying unobservable concept. This relates to measurement in the social sciences because often what we measure in it is unobservable. Often in psychology, we cannot directly measure constructs. Two important properties we need to understand regarding empirical measurement are reliability and validity. Reliability concerns the extent to which a measure yields the same result on repeated trials. The more consistent repeated measures are, the more reliable the measurement procedure. While a method may be reliable, that does not necessarily mean it is accurate or valid. Dawes gives an example of this in height measurement using a rating scale rather than a ruler. Validity concerns that a measure actually measures the concept it intends to. Now let's first take a look at the data we have, which contains 30 observations of 13 variables. 10 of these variables are scale items, which are the only ones I have displayed here. Those are the values that we're going to focus on for now. You can see that the means are varying quite a bit, but they are mostly negative. The standard deviations range from around 0.73 to 0.91. And you can also see here that our standard error is minimal and relatively equal. Skew and kurtosis show that we have a relatively normal sampling distribution, so we can move forward. Let's circle back to reliability before continuing with the data. One of the ways we can measure reliability is using classical test theory. The formula displayed, O equals T plus E, is observed score equals true score plus error, which shows us that variability in our observed scores is a function of some underlying true score plus error. It's crucial to note that all measurement contains a certain amount of error. There are two types of measurement error. Random error, which is any chance factor that confounds a measurement. This is inversely related to the degree of reliability of the measuring instrument. Here, to test reliability, I used R to run Cronbach's alpha. First, I need to mention that we did have some negatively correlated items depicted with a dash next to them. So we see variables 2, 5, and 8 are negatively correlated, which I corrected for, and that left us with an alpha of 0.92, which is pretty good. Another important thing to mention here is that Cronbach's alpha is especially sensitive to sample size. We cannot have less than 10 sample items, so we will not remove any items here. Below, you will see reliability if an item was dropped, but because of the sensitive nature, we are not going to do that and risk alpha being skewed. It is also important to mention that although alpha is referred to as the estimate of reliability sometimes, it is not the only estimate of reliability. Cortina. Here I have a correlation matrix to better depict how the variables correlate. There's a good mix of negative and positive correlations, which you can easily see here. Blue shows positive correlations, and the more orange-pink color shows negative correlations. The correlations range from around 0.4 to 0.75, and this is going to be considered a moderate or strong relationship between variables. On this slide, I neatly organized some hand calculations I completed on another set of data. I show the values on the top left side and the difference if each item were deleted on the top right. Then as you look lower, calculated I calculated the covariances and item total correlations. Covariance shows us the relationship of two variables as one of the variables change. Item total correlations show us how highly correlated each item is with the overall scales. This is just to give a better idea of correlations and how changing variables affects data. Now we will return to the data in question. Taking all of the information I have just shared with you, we can determine that our scale checks out, and we're going to proceed to hypothesis testing. To begin understanding hypothesis testing, we need to first understand the two types of error. Type 1 error, which is a false positive, and type 2 error, which is a false negative. We correct for risk of type 1 error with p-value and power, while we correct for the risk of type 2 error with power and effect size. Here I ran a two-sample t-test. Group 1 indicates females and group 2 indicates males. We are looking here for the effect of sex on outcome Y1. These are the variables that I took out of the data I was displaying on the first slide showing data. There is a significant difference here as shown by the p-value 0.00211, so we can reject the null. If you look at the means, we see that males have a higher mean on the variable y1 than females. To determine how meaningful the difference is, we need to use Cohen's d and calculate the effect size. Cohen's d is the difference between two means, which you can see here in my hand calculation I have, and that comes to 0.87, and then we divide that by the pooled standard deviation, and our effect size comes up to 1.24. which is a large enough effect size to calculate the power. But it does go against Cohen's recommendation that researchers should report effect size as a confidence interval. We're just going to ignore that, though. And then on the right of my hand calculation, you will see that the power comes to 0.91, which is going to mean that it is close to 1, and we rejected the null correctly. And the effect size lets us know we can rule out type 2 error. That is my Module 2 demonstration. Thank you for listening.